Hi, I'm Bill, and I'm a senior majoring in actuarial sciences.
Hi, I'm Jan. I'm a sophomore majoring in applied mathematics, and today we'll be presenting no-slip billiards. I'll start with the introduction. Mathematical billiards are physical systems studying particle movement. There are two main ways of looking at these systems. First one is looking at the trajectory map, which describes the particle movement in bounds. The second is the phase space, which describes the relation of the particles' velocities at collision. A lot of study has been done for the specular variation. In the specular variation, there are known ergodic cases, for example, Sinai dispersers and Bunimovich stadium billiards. There are also known examples of integral phase space, such as ellipse and circle billiards. The variation that we are interested in are no-slip billiards, which are dynamical systems of freely moving rotating particles with various mass distributions in a rough bounded region, and they reflect according to the no-slip model which preserves all energy. Naturally, questions arise whether the behavior of specular billiards apply to no-slip. We seek to answer some of questions whether there are any cases of ergodic or integrable billiards. I'll let Bill to tell you more about our results.
So we use simulations in Python and SageMath to examine orbits from various launch trajectories and phase portraits. Trajectories provide information about ergodicity by launching a particle from a given position and angle with a given mass distribution, which we observe. The first set of figures here in the results section are the images for a single launch trajectory of a particle in a table. Through our simulations for some regular polygons, such as the triangle, square, and pentagon, we found mass distributions for which the phase space consisted of persistently periodic points. Now for the phase portraits themselves. Phase portraits encompass millions of orbits for overall conclusions of structure for a table or family. We mainly considered 1 and 2 parameter families of tables in our research. Varying these parameters could take a table from more ergodic and chaotic to more structured. The two phase portraits depicted here are the product of varying the distance between a union of two circles from positive to negative, taking it from the shape of a Venn diagram to more of a lemon. Another example are the previous curved and non-curved regular polygons. Number of sides and angle of curvature affect ergodicity. In the future, we could investigate more tables and offer more formal mathematical proofs for our findings.
Applications include many systems involving particle movement in a closed space, such as lasers or microwaves. This research is important because it can be used for reference for future billiards investigations.